me write down E plus first. Would be 1 over 4 pi epsilon naught. 1 over 4 pi epsilon naught times the charge itself, right? Q divided by r squared. Now, what is r? How far is this point from here?
Y.
Y
Oh no.
minus
Y minus S.
S.
Y minus s over 2. Yeah, right. So y minus s over 2 squared, right? So distance squared. Yeah, y minus s over 2. That's this portion. Y, which is s over 2, so you subtract that much. And it's in the positive y direction, so I will just keep it plus, right? The positive direction. Okay. How about E minus, the electric field due to the minus charge? It would be, well, 1 over 4 pi epsilon naught. The charge has magnitude Q also. I will worry about the direction in 1 second. But how far is it from the point? How far is the negative charge from here? Yeah, it's y plus this portion, which is s over 2. So y plus s over 2. Y plus s over 2. So the total electric field, oh, and I said, let's worry about the direction in a second. Well, let's worry about it now. In what direction is it?
Negative.
Minus, so minus, okay, yeah. Okay. So there is a minus. So the total electric field, we will add them at the two electric fields to get that. And so the total electric field, okay, the total would be E plus the negative electric field. So you would have this. See, both of them have Q over 4 pi epsilon naught. Q over 4 pi epsilon naught, so I'm going to factor that out. So Q over 4 pi epsilon naught times this one, you will have 1 over y minus s over 2 squared. 1 over y minus s over 2 squared, and then minus, right, minus, for this one, that's where the minus sign comes from. And this one is 1 over y plus s over 2 squared, right? 1 over y plus s over 2 squared. Now I just need to make a common denominator for these two and add them and simplify a little bit. And hopefully it will simplify. Okay? It will simplify to a reasonable amount. Okay. So you get E equal to Q over 4 pi epsilon naught. Okay. The common denominator would be the product of the two denominators, right? This one times this one. So that's y minus s over 2, and then squared, and then y plus s over 2 over squared. And then you do 1 times this one, and then minus 1 times this one, right? So when you do that, let's FOIL the expression right away. So first on here, positive 1 times 1 plus s over 2 squared. So you get y squared plus twice y times s over 2, and then plus s over 2 squared, isn't it? Okay, so you would have this. You would have, from the first one, you have y squared plus twice y times s over 2, that's just y times s. And then plus s over 2 squared, which is s squared over 4, plus s to the second power over 4. And then minus, so there is some algebra here. Yeah. And then minus 1 times this. So let's FOIL this one. Let's FOIL this one. So I get what? Y squared.
Minus ys.
So we look like this one, but with a minus sign in the middle, right? Yeah. So it would be y squared minus ys plus s squared over 4. So look at this, what cancels and what stays?
The y's cancel, the s.
Yeah, you got y
Over
squared
4.
minus y squared, thank you. And then, let's look at the s squared over 4 minus, and then there's s squared over 4, so that cancels. And then ys minus ys, that becomes ys plus ys, which is
2s.
twice ys, yeah. So you would have this, e would equal to q times s times 2, right? From the ys there, over 4 pi epsilon naught, that's that. And then here I have 1 over. Now this one looks like y minus s times y plus s, the whole thing squared. Right? A plus b times a minus b would be a squared minus b squared squared. This case, because we have y minus s squared and then y plus s squared. So that's y minus s times y plus s, the whole thing squared. Yeah.
What happened to the y? Do we need it?
Oh, I'm missing a y. Yeah,
Oh, you were.
you're right. Yeah. So there is a y. Thank you. Yeah. Let's put it here. Well, y times s. Yeah, let's put it there.
Can you like raise the board up a little bit?
Yeah. Is the table on the way? This big table?
It's just like, from my angle, it's
Okay.
very hard to see the bottom part of it.
Right, yeah. So this is the ys. So when you follow this one again, you would have this. This squared, you would have y squared minus s squared over 4. Okay. Okay, so again, I mean, so today you can expect this. It's all calculations. All we'll get some integrals and
There we
it's
go.
gonna be really dry.
Okay.
So now, this is the exact field on the y-axis, on the axis of the dipole. But usually we would like the approximate field. What is the field approximately if y is much larger than s? So let's say this is s. Maybe s is like a centimeter, and y maybe is a meter, 100 times larger.
Right.
So if y, let me come here. If y is much larger than s, this is not just larger, it's much larger. So if y is much larger, so what can you conclude about y squared when you compare it to s squared? So let's say s is 1 and y is 100. So 100 is much larger than 1. But how about 100 squared compared to 1 squared? It's even much larger, right? You would have, instead of 1 to 100, it's 1 to 10,000. So you can just ignore this one.
Okay.
So
Nice.
here, this one is approximately, can be just neglected compared to y squared. Okay? Compared to y squared, it's negligible. So I would just have in the denominator now, if I neglect the s squared, what would I have in the denominator?
Y squared.
Yeah, y squared squared, so that's y to the 4th. But I have a y here on the numerator, so what do I end up with?
Or y cubed.
S over y cubed, right? Yeah, it'll be a y cubed. So that's what I'm going to write. So again, we neglected this, so it becomes y squared squared, so that's y to the 4th, but I have a y here, so I can cancel one of the powers, so you get y cubed, and there is an s in here. So you get the electric field then will be approximately, or this is on the axis, so approximately, I should write a line like that. So it would be 2q, 2q, and then s, and then over 4 pi epsilon naught, and then y cubed. Okay, this is on the axis of the data. Yeah.
And is that for every situation? Okay. And then,
As long as you're on the axis.
oh, on that axis, okay.
On
And
the
then
axis.
we're assuming that the particle at that point is positive, that's why it's getting repelled, or is it just in general throughout the field?
This is, there is no particle here yet, it's just the electric field.
Oh, okay.
Yeah.
That makes
the
sense.
electric field.
Okay.
Yeah, if you were to put in a particle there, the force on it would be the charge of that particle times whatever this electric field is.
Okay, that makes sense. Thank
Yeah.
you.
So now, I'm going to, now define the dipole moment. Dipole moment,
You might scooch it over a little bit.
can I do one?
Sorry, I can't really
Yeah.
see the equation.
So this is E approximately equal to 2qs over 4 pi epsilon naught. Yeah. So let me just write it here. So we have E is approximately equal to 2qs over 4 pi epsilon naught, and then y. Okay, so now we're going to define the dipole moment. Dipole moment is given the symbol P. Is P, and it is it has a magnitude of just q times s. Q times s. So q is the charge, and then s is the distance between the two charges. So qs is q times s. That's the dipole moment, and it's a vector. And that vector points from the minus to the plus, so it points this way, from minus to plus. So that vector will point this way. So, with that direction in mind, so it's pointing in the positive y direction, right? Positive y direction. So we can write the electric field as, now with the vector on it, 2, again, what's qs?
P.
It's p, yeah, p. And I'll put a vector sign on p, because it points in the correct direction, it points in the direction upward, in the direction of the field, divided by 4 pi epsilon naught y squared.
Isn't Y cubed?
Y cubed, yeah. Okay.
You can just get rid of 2, right? Because this
We
is
can
4.
get rid of 2, but for now we don't want to.
Oh,
Yeah, we want to keep the 2 at the moment, yeah. But yeah, so, now how about if I orient my dipole instead of the y-axis, I can orient it in any direction I like. Let's say I orient my dipole this way. Here's a minus, here's a plus, and I'm going to orient my dipole this way, in this r direction. What would the dipole moment be?
The distance between.
Just replace
Which one?
y with r.
We just replace y with r, yeah.
Wait, can you explain again?
Yeah, so earlier I chose my dipole this way, along the y-axis, right?
Yeah.
What if my dipole actually points in another direction besides what I call the y-axis? Well, it will be exactly the same, I just have to look at it. If I take this board and move it this way, is anything going to change?
No.
No, so the electric field now would point along the line of the dipole, right? Along the line of the dipole.
Wait, no.
So what happens is this, you will just write E, will just be, instead of just, this is the R axis if you like, that's R, the R direction. So it'll be 1 over 4 pi epsilon naught, and then 2p over R cubed. So that's the electric field due to a dipole. Due to a dipole along the axis of the dipole, right?
Okay.
On the axis of the dipole, yes.
Why did you choose dipole towards plus instead of towards the negative?
What if what?
Why did you choose dipole, the direction of dipole, towards, like, going towards positive x, y axis?
Convention. It's a convention. You're saying, why can't we choose it this way?
Yeah.
You could,
Oh.
but the agreement is, this vector is a vector that points from minus to plus.
Also, is it gonna be given in the question, or
Huh?
is it gonna be given in the question, or it doesn't really?
It is assumed to be in that direction.
Oh,
Yeah.
okay.
Okay. Now, how about the dipole? Now, if I want along a plane that bisects the dipole moment, the center of the dipole moment along this plane. So now we did this, right? We did the one vertical. How about the one on a plane like this? Let's look at the x-axis, because the x-axis will be on that plane. So how does the dipole, how does the electric field look like? And I'm going to, I'll do it on the top one. Okay? Or maybe I will do it on this board because it, we will refer to this later. Yeah, let's do it on that board. So here's the question. So here's the question. Here is a dipole. Here is a plus. Here is a minus. Their distance s apart. Here is the y-axis. Here is the x-axis. Right, this is s over 2. S over 2, and of course this one is also s over 2. Okay. So let's see what is the electric field due to this dipole here at this position. Let's say right? From here to here. What's the electric field? Let's look at the electric field from the plus charge first, and then the electric field from the minus charge. The electric field due to the plus charge would point in what direction here? So in general, electric fields point away or toward pluses?
Away.
Away. So here's the plus, draw a line from it, all the way here, and then away from it means this way, right? That's the electric field due to the plus charge, and it's in that direction. So let's call it E plus. And the electric field due to the minus charge will point toward the minus. So here is the minus, and toward means this way, right? So that's E minus. E minus. Now, what do you notice? Both of them have a negative y component, but one of them has a positive x component, right? This one points to the right and down, and this one points left and down. So the right and the right, they cancel each other, because the distance from here to here is the same as the distance from here to here, and the charges are equal in magnitude. Right? One of them is plus, the other one is minus, but both of them have a charge q in absolute value. So the x component cancels, and I just end up with an electric field that simply points this way. So one due to the minus and one due to the plus. That's the electric field. The net electric field will point down. So, and we would like to find out how much, or what is it. Hint, it will be similar to this one. But if I remember correctly, there would be no, it would just be no 2. There will not be a 2. So let's see if my memory is right. So let's do it. Yeah, let's do that one. And I want to make sure. Electric field. Yeah. 23. Yeah, so, okay, good. I'm just worried that I'm behind where I wanted to get to. Okay, so from here to here, the distance is, what's the distance from here to here? If this is x, this is s over 2, so it's
X
X
squared
squared plus
s
S
squared
squared
over
over
4.
4, square root of it.
okay, s squared over 4, like this, and square root, right? That's the distance, yeah. And the same thing from here, right? It's the same distance, so whatever. triangle is called, yeah. So the electric field due to the plus charge, the electric field due to the plus charge, the y component, I would call it the y component, E plus y component. Right, the y component, it will point downward, and so that's the negative y direction, right? So I'll put a minus sign myself, because it points down in the y direction. And it's equal to, the electric field is always 1/4 pi epsilon naught, and then the charge divided by the distance from the charge to the point I'm interested in, squared. So the distance is this square root. So when you square the square root, you just get x squared plus s squared over 4, right? So you get x squared plus s squared over 4, that's the distance squared. And then, I'm not done, this component is, if this angle here is theta, this angle here is theta, this angle here is theta, so it will be times the sine of theta, right? The adjacent will be the x component, but we said the x components cancel,
Oh, I see.
just only the y component, so down. So times the sine of theta, but what's the sine of theta? Sine of theta, you can look at it from this side, it's opposite over hypotenuse, right? So it's s over 2 divided by the hypotenuse. So s over 2 over this. So it will look like this. S over 2 divided by x squared plus s squared over 4 to the power 1/2, right? So square root means power 1/2. Multiply these, and you get to the power 3/2, right? To the power 3/2. And so you would have 1/4 pi epsilon naught, and then q, and then times s over 2 divided by x squared plus s over 2, s over 4 squared to the power 3/2. The electric field due to the minus charge now. Electric field due to the minus charge in the y direction. Oh, I forgot a minus sign, right? There is a minus sign. Now, due to the minus charge, does it point also in the negative y direction or differently? What did we say? Yes, it points in the negative, both of them points in the minus. So the y component of the electric field due to the negative charge also points down. So it's down. So minus 1/4 pi epsilon naught, and then q divided by the distance, it's exactly the same distance, x squared plus s squared over 4, and then times the sine of the angle. But this angle and this angle are all exactly the same also, because the, what do you call it, isosceles triangle? It's two sides are equal, that's what it's called?
Yeah.
Yeah, I forgot. So it's the same angle, so the same sine. So times this same, so s over 2, x squared plus s squared over 4 to the power 1/2, and so it's also, I said minus sign, so minus 1/4 pi epsilon naught, and the q times s over 2 over x squared plus s squared over 4 to the power 3/2. Now the total electric field, you will be adding these two. Both are negative, so the overall electric field will be negative, but they're exactly the same. So when I add them together, what do I get? I just get twice whatever each one of them is. So you get twice. So the twice, you got s over 2 in the numerator. If you twice it, just the s over 2, the 2 here goes away, and I will write exactly the same expression, but without the 1/2 when I add them both. Okay. So in other words, the total electric field will be E plus the y component plus the E minus the y component. When you add them, both are exactly the same quantity. So minus 1/4 pi epsilon naught, and then I have q times s, and then x squared plus looking at the electric field far away from the dipole, meaning if x is much larger than s over 2. So if x is much larger than s over 2, then x squared would definitely be way larger than s squared. Okay? So I can, again, ignore this one. Ignore this one. So now what do I get here? If I ignore the s squared over 4,
X cubed.
yeah, I'll just get x cubed, right? X squared to the power 3/2 is x cubed. So I would have electric field is equal to 1 over 4 pi epsilon naught, and then q times s over x cubed. Okay. So now the thing, the dipole doesn't have to orient vertical like this, it can orient in any direction. So what's the electric field in that case along the plane that bisects the dipole? You can just replace x by r. Oh, I forgot a minus sign, is that why everybody? Okay, yeah, there is a minus sign, I forgot. And so in that case, the electric field will just be minus 1 over 4 pi epsilon naught. What did we say q times s is defined as? P, yeah, P. And then P over R cubed. Okay. So this is the electric field that points in a direction that is the electric field on a plane that bisects the dipole moment. Okay, so I'm going to continue. I have, yeah,
Can you just explain why you mark side theta? I mean, like the first one, like s half, no, all the way up, to the left, to the up.
Here?
Yeah.
Uh-huh.
Why did you times that? Can you explain it? Like,
this should say S over 2.
yeah, I mean, like, why
And
did you
then,
do that?
oh, when I added them, why did I times by 2? Time it by 2?
No, like, why did you times the entire, that, like, the angle?
Oh, so I had this, why did I multiply by
Yeah,
this?
yeah,
Okay. Yes, so the electric field points in this direction, right?
yeah.
So it has an x component and a y component. And this electric field also points in this direction, so it has an x component that's opposite to this one, which exactly cancels it. But it has a y component this way. So I found the y component of each electric field.
Yeah.
And the y component means I multiply the magnitude by the sine of this angle theta. So this is theta, what's the sine of theta?
Oh,
It's the
okay.
opposite over this one.
Okay, got it. Thank you.
Now, these are discrete charges. We will come back to the subject of the dipole toward the end of chapter 23. We talked about the potential energy and torque of a dipole in an electric field. And so that would be, so we're not quite done with dipoles yet. We'll revisit it. And then we will do the, now continuous charges. Yeah.
If that problem is the place bisecting the dipole, what would the other problem be?
That one would be along the line joining the dipoles. Yeah. And then there is a problem where at any point in space, where if it's not the line joining versus the bisecting, there is a general expression for that. But we did just two special cases. Yeah. Okay, so now charge distributions. What if you have a continuous charge density? I mean, a continuous charge distribution. You don't just have a Q here, and a Q there, and a Q over there. What if I have just a line of charge, or a surface of charge, or a disk of charge, or a ring of charge, or whatever? How do I deal with that? Well, the electric field, or the force, the electric field due to several charges will be the vector sum, right? You add all the vectors from each charge. So the electric field for a continuous distribution will be, instead of summation, you would have integration. The continuous sum, right? Riemann sum, yeah. So that's what we're going to look at. So let's first define what lambda and eta are. This was O. So if you have a linear charge density, then you would like to talk about the charge per unit of length. You will have lambda, it is the charge per unit of length. Meaning, if I have a 1 meter long of charge, how much charge is in that meter? Like how closely packed are the charges? And we did this last semester when we talked about waves on a string. We said mu was the mass per unit of length, right? If you have like rope, if I give you several meters, 10 meters of it, how many kilograms is that 10 meters worth? And so you take the way to calculate the charge, the mass density in that case, you take the total mass and you divide it by the length of the string. So the same thing here, you take the total charge and you divide it by the length. So the units will be coulombs per meter, right? And then you have surface charge density. Surface charge density, and the symbol for it, the author gives eta, and it is, and we had the symbol eta, yeah, for the efficiency of engines, right? We used that, yeah. So other books usually use the sigma for charge density, for surface charge density, but we have eta here, no problem, and it is charge per unit of area. Charge per unit of area. So it'd be coulombs per square meter, right? Coulombs per square meter. So, I mean, if you have, let's say you take this one sheet of paper, and you ask what's the mass of this sheet of paper. So if I weigh it, put it on a scale, let's say it weighs 2 grams, I find the area of this sheet of paper, and I divide the mass over the area, and that's my area mass density. Same thing, if I have 1 coulomb kind of smashed or smeared on this sheet of paper, then if I were to cut just 1 square inch, how much charge do I expect to have there if it's uniformly distributed? And so it's you multiply the charge density by the area, and that will give you how much charge you have per square inch, or per square foot, or per square meter. Does that make sense? Yeah, okay. So we like to have those. So the first problem would be this. If you have a charge density, let's say I have a positive charge here. Here it is. It's a line of charge. Let's say it's plus, 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 plus. So you see, it's not just one plus charge of lots of them. But it has a uniform charge density. So let's say it has lambda. So every meter you can expect to have a number of coulombs per meter. For every meter you cut, it has a set number of coulombs. So now let's say this is the x-axis. Here is x equal to 0, here is 0. And the question would be, so this one has charge density, lambda. If I am a distance r away, so from here to here, it is r. And I sit here and I ask, what is the electric field a distance r away from this line of charge? And this line extends to, let's say, minus infinity this way, and it goes to plus infinity that way. So it's an infinite line of charge. So what is the electric field at a particular point? A distance r away from this line. So the way you do it is you will ask, you say, okay, let me say I'm right here at this particular portion, right? There will be a charge here, a certain amount of charge within this dx, this width of dx. Right here, this is x. There will be a charge dq here, right? There will be a small charge dq, and it will produce an electric field at this point. So every little charge will produce a dE, a small amount of electric field, and since it's, let's say, positively charged, the electric field will look like that, right? dE, in that direction. I call it dE because it's not the whole electric field, it's the electric field due to just this. And by integration later, we will get the total electric field. Okay? So, what is the electric field? Let me write it down, or before I let me write down how much is the electric field there due to this little charge. So dE will be I'm looking for here is the electric field formula. 1 over 4 pi epsilon naught times the charge divided by the distance from the charge squared. Now the charge, I don't have a total Q. I have a small amount of charge, not Q, so I'm going to call it dQ. So I have the 1 over 4 pi epsilon naught, and then I have dQ divided by the distance squared. Now what's the distance? Well, distance from here to here. So if this is x, from here to here is x, and this is r, then this distance is, let's call it distance squared. It's equal to r squared plus x squared, right? So that distance is d. So d squared is x squared plus r squared, or r squared plus x squared. Okay. All right.
Would that be squared as well, or did we already take care of it? Like the x squared plus r squared, does that need to be squared in the formula as well?
It's already squared.
So, I see what you're saying. Okay,
Yeah.
that makes sense.
Yeah, technically it's like this. D is the square root.
Oh yeah, okay, that makes sense.
So when you square it,
You
the
square it
square root
together.
goes away. Yeah.
Thank you.
Okay. Now this is the electric field, and it points in this direction. Now if you have a dq here, there will be another dq on the other side of the line, and it's right here. Here is a dq. It will be the same distance, but it's on the negative x direction. But it will produce an electric field away from itself in this direction. So one of them produces an electric field to the right and upward, the other one produces an electric field to the left and upward. So the left and right, they cancel each other because they happen to have it's the same magnitude, the same angle, but one of them is in the positive direction, the other one